general metrology lab up towards our tribology lab, where a profile meter, which is used for roughness measurements, are located. Also the one over here, like next to me, and the third one in another corner, but it's far away, hard for you to see. But yeah, so also in this lab, I have some additional things I wanted to show you during the speech. So I'll be sitting here. So to begin with, basically, I just wanted to show you that I don't know, maybe some of you already noticed that I've uploaded some of the videos already watched regarding the what is like the basically metrology in general, like, and mostly it's related with the GD&T, because I think in many ways it's one of the most important aspects of metrology is this geometric dimensioning and tolerancing, how to understand it, how to properly read it from drawings, and how to interpret it properly. So, and I also yesterday added the educational posters. So basically, when you click on them, you'll get like posters. They are originally like A1 sized posters, but you can like use them digitally. I guess you won't print them out, and I wouldn't do it either. But why I wanted to share them with you, because there are like tons of small good information collected in those posters related to different type of tools. So for instance, this is about the outside micrometers. We are about to look at them in our laboratory. So here you can already check the terminology, like this is the anvil, this is spindle, these are measuring surfaces, etc., etc. And there are a lot of good tricks and tips how to use them properly and how not to use them in certain cases. Same, we have like a poster for a hardness measurement. So if you are dealing with some sort of like a hardness value, let's say in the tensile strength, like a scale, then by using a table like this, you can approximately see how much it's in the different measurement scales, like instance Vickers or Brinell or Rockwell scale. So then about height gauges. So same story, how to clean them, how the components are called, and like what to do and what not to do. And more importantly, I think for the small tools like caliper, it's yet again how to take care of them and how things are called, and you can also see different types of them. So it's kind of a nice small let's say review type of paper poster, which can really highlight you some very basic very important stuff about all the typical measurement tools. And one of the last but definitely not least is like a whole poster all about roughness standards, profiles, parameters, etc., etc. But as I promised, today we will deal a lot of about roughness. So we will look at all of these features step by step. But now here you just see a very nice like a review of the thing. And here is yet again about the GD&T symbols, etc. Flatness, cylindricity, and so on. And here are some schematical examples, how it's measured, how it's shown on drawing. So I think this is a nice kind of thing to look at when you're preparing for an exam or my small test. So they are free of charge, available here. Use them, look at them, and simply get smarter. So okay, that's that now. But Today I'm actually gonna show you a very long presentation with some small animations. But before I start getting into the presentation details, yet again, I simply checked what's available on YouTube, and yes, there are a couple of videos like this one, like what is surface roughness, and this actually I'm about to show you because it's very relatively short, and it kind of, I think it's very nice to show it in the very beginning, so you have some sort of like an overall impression, like what we are about to look in more details. This we will get at a certain point. This will simply compare two types of measurement tools. And here, these ones I won't show you, but I simply wanted to show you that they exist on the YouTube. So if you want to, you can, for instance, look up the 3D optical profilometry 1 hour long like a webinar, which goes yet again step by step with a lot of examples and explanations what is what. Same here, half an hour presentation of what is roughness and how it's interpreted and so on. So this is similarly as for other things we've looked at this subject. If you want to, you can easily search up an information, either it's like here in the YouTube, or you can also Google it up in a text version. So the most important thing for me is just highlight you that this information exists and how to find it. So, and as I mentioned in the very first lecture of mine, that difference from high school and university is that in university, us as lecturers are more interested to kind of encourage you to search up for the information yourselves, and we are here only to supervise you and guide you in the right direction, point out like what is useful information and what is garbage. Luckily, in our like field, I haven't ever actually stumbled on false information. So basically, there are tons of fake information and basically false claims about all sorts of stuff, the conspiracy theories, etc. Luckily, no one wants to conspiracize metrology so far. So thus, I think if you will use keywords like the metrology, GD&T, and for in this case surface roughness or surface texture, you will get a very reliable source of information. And I really encourage you also to take advantage of this like a 21st century possibility to look up things which you don't know. You simply need to know that such information exists, and that's why I'm here. I'll try to help you out with this. Okay, to begin with, I think I'm about to show you this 7-minute video. It will kind of quickly, yet again, summarize what is what, and then we will break it down to a very small fractions step by step. I'll go through a very long presentation, and I guess we won't deal with it in the first lecture, so we'll have a break. Then I'll continue as much as needed, and then that's it for today. So okay, now just enjoy video, and we continue further on afterwards.
Surface finish, surface texture, surface topology, surface roughness. What does it all mean? Let's find out. Welcome back to Star Rapid, where we're serving up a potent brew of serious engineering for serious engineers.
Serious engineering.
My name is Gordon Stiles, and that's actually how you say my name. And I'm the CEO of Star Rapid. I've been in engineering for over 30 years and run multiple companies working with prototyping and low volume manufacturing. And today we're going to get seriously superficial.
I saw my spinning instructor wearing it and I was like, shut up. Where do I get that?
You get it? Nope. I told you they wouldn't get it. Anyway, we know that talking about surface finishes can be tricky and often leads to confusion. To make it a little easier for product developers and engineers to understand surface finishes and how to communicate about them, we'll start by defining some of the terms around this subject. First of all, what do we mean by surface finish? Surface finish is simply the condition in which you find the surface of a part at any point during the manufacturing process. This could be a primary finish, such as you'd get from a pair of rollers in a rolling mill, or it could be the finish you get after aluminium is extruded through a die, or the finish on a sand casting before any post-processing. Next, there are secondary surface finishes created during CNC milling, turning, grinding, sanding, lapping, or polishing. Each of these processes will impart its own characteristic finish to the surface, leaving behind a fingerprint of sorts on the workpiece. Then many flavors of tertiary finishes used by other treatments. Examples here: various chemical passivation techniques like anodizing or galvanizing, electroplating with chrome or nickel, or decorative surface coatings such as painting or powder coating. Surface finishes can also be transferred from one part to another. For example, when the machined core of an injection mold tool transfers CNC tool marks onto the inside of the plastic part, the plastic part would then have a surface finish that looks like it had been machined when in fact it wasn't. Is that clear? I hope so, because now things start to get really weird. Okay, how about surface texture and surface topology? In general usage, the term surface finish is pretty much interchangeable with surface texture, surface topology. Topology literally means the way in which something is arranged. So in this case, it means the way in which material is arranged on the surface of a part. In most cases, texture and topology are talking about the same thing. But in engineering, we want to be like the cool kid who doesn't follow the rest of the gang. So there is a special usage of surface texture to describe one specific result. If a surface is bead blasted, or if a piece of metal is spark eroded using EDM solid zinc to make a spark finish, then you end up with a stippled surface finish just like this. Engineers in the prototyping and low volume industry often just call this incorrectly a texture finish. So that one is a bit confusing. What about surface roughness then? Surface roughness is a bit different. This is quantifiable using a numerical unit called RA or Ra. It's derived from measurements made of the surface profile using one of several different techniques and types of instruments. Some of these are contact type, using a very sensitive probe or stylus. Others are non-contact, using optical light, lasers, or even X-rays. In all cases, Ra, not to be confused with Ra, is a calculated average between peaks and valleys of the surface. Firstly, a mathematical filter is applied to lop off the very high and low numbers, which might indicate random aberrations that don't represent the true surface roughness. Secondly, to make sure that Ra is accurate, multiple readings are taken so that the measuring instrument captures as much unique data as possible. In this graphic, you can see a cross-section of a surface. As mentioned, rough. And so this line will fluctuate over a given distance. Roughness spacing is the grooves or their frequency. The lay is the dominant direction of the grooves. And then there's waviness, which is more like a periodic repeating distortion over a longer sampling length. So a low Ra value means little deviation or a very flat or smooth surface, while higher numbers are rougher. Product developers need to know which Ra value they want so that they can communicate that to their manufacturer. But we must point out that it doesn't make sense to specify an arbitrarily low RA number just for the hell of it. The costs associated with making finer finishes go up exponentially as Ra numbers get smaller. And this is regardless of the manufacturing process used. This also applies to production lead times. So only specify low RA values if it's absolutely for your product application. Otherwise, you're just wasting time and money. At Star Rapid, our standard roughness for CNC machine parts is RA 3.2 microns, but we can do as fine as, for example, 0.2 microns on a CNC machine. But it might take 10 times longer and cost 10 times as much. So please try to stick to no finer than 3.2 microns unless you need it. One final thing I would like to show you is this. This is a set of surface roughness samples. The cost will be anything from $100 up to about $350, depending upon the material they are made from. This set happens to be made of nickel, so it doesn't rust. I think that every manufacturing engineer who deals with CNC machining should have a set of these. You just look at your part and run your small pinky fingernail along the surface of the part, and then find that similar look and feel in the sample set. This is a really quick and relatively reliable way of knowing if your supplier is achieving the general roughness you require. Okay, that's all for this episode. In a future video, we will go into even more.
So that was a kind of quick summarize of what we are about to deal with. And the reason, I think I already mentioned it, but why I am paying so much attention to this roughness issue, specifically in your specialty, because in the medicine and biomedicine, this surface finish plays a humongous role, and specifically if there is some interaction with your some sort of a designed component and the human body, this surface texture plays the important role of how it will feel. Either it will be antibacterial or not, is it will be easy to clean or no, and so on and so on. So thus it means that your specialty needs an extra care, like an extra information to really understand it, because I've also, I think I mentioned that oftenly from people from your specialty, either bachelor students or more oftenly masters or PhDs, visit this specific lab which I am sitting in right now in order to take roughness measurements for their samples. Either it is like a parts of a bone or teeth, or sometimes it's some sort of a glass surfaces on which the bacteria is afterwards grown, and so on. So there are also, we had cases with the calcium apatite, it's this artificial bone samples, and so on. So this means that yeah, your specific specialty really considers this surface finish, and it's important to know at least the basics about how to understand it and also how to measure it properly. So before I get to presentation, I just simply wanted to show you that for instance, this some sort of like a wavy waveform is actually measured on a sample which looks like this. This is a classic rounded cylindrical workpiece. Okay, it's very hard to see through the screen, but it has this periodic oscillation on the surface, and I can even stretch it with my nail and feel it. Then surfaces can be way different, like for instance, we might have a profile like this, which looks pretty much like some sort of like a sound wave instead of being part of a surface. Yet again, something similar with a bit less distorted. And the last but not least, pretty much the similar to the first one. It's it again, a very periodic sharp asperities, but they are not that even. Some are smaller, some are larger. So what this is actually nothing else but a simple cross section of our surface. Let's say we have a workpiece and I am using a profile meter, which we're about to discuss later on, and I am mechanically kind of scanning one cross section line of my surface, and I am getting as a result this instant magnified version of my profile. So honestly, it's very hard to imagine that any surface is this rough, but this magnification in the vertical direction in this specific case is uh, 2000 times. So basically, sorry, it's 5000 times. So basically, you take this profile, like shrink it down 5000 times, you have the actual, like a real scale interpretation how smooth or rough your surface is. Uh, why roughness is so important? I already mentioned that. First of all, it changes the feel of the product. So if you are like touching something and if it is rough, then you can immediately feel the grip and kind of texture squeezing in your skin. If it's smooth, then you are already like sensing it that it is smooth, but it still could feel kind of grippy because now this very smooth surface have molecular pulling forces working in your skin. But what is even more easily noticeable that these very smooth, polished, mirror-like surfaces very nicely immediately show you some sort of like a fingerprints if someone touches it, while the very, let's say, rough surfaces don't show anything. And this is an example. Hope you will be able to see. This is a surface which is slightly mattated. You can see the lamp reflection, but I cannot actually see the lamp itself, and I can like touch it and you can't really see my fingerprints anywhere. While if I take same workpiece but it's now mirror like polished, you can actually now see my ceiling, and there's a lamp, and there's a like another parts of the ceiling. And if I do like this, then you see immediately my fingerprints. And sometimes it is very important that you are able to see whether someone touched something or not, specifically nowadays when there's like a pandemic and people are very aware that microbes and stuff like that exists. So in some specific cases you would be interested in spending this extra money to prepare this surface as smooth as possible to kind of show you that someone touched it. And also you don't need to be a scientist to kind of at least predict that if the surface is more robust with the more of these oscillations like shown here, it's easier for bacteria and microbes and all sorts of other particles to kind of stuck inside this texture and start to grow there, so start their development. While for the very smooth surfaces, they might maybe fall down, or it's a smaller chance that they would achieve such a concentration that they could start growing. So that's why it's so important to prepare surfaces in a certain way. Of course, those of you will maybe focus somehow on the like artificial teeth or bone structures. It's yet again very important to produce these artificial tooth replacements in a specific roughness range. So why? Because if it will be too rough, same problems. You could like feel it that your gums are rubbing against the very rough surface, and your body would basically react in different ways. Uh, while making it too smooth be insanely expensive. So thus it turns out that there is actually a standardized roughness value for a human teeth replacement. And if you want to deal with this, then you also must be aware how to measure it and that such thing exists. And the same is true also for artificial bone and hip replacements. So it's the same story. If we have an artificial hip, let's say, it is in the friction pair with a second surface, and you need to have a certain amount of roughness in order to make sure that there can be a little bit of a lubrication in between those two surfaces, because if it's too smooth, then if we squeeze too insanely smooth surfaces together, it would squeeze out all the moisture and lubricant in between those surfaces. So thus, we are actually interested to keep some roughness, but to keep it in a very specific way. Because let's say if this is our, okay, this is not maybe the best example, but so it is also important to see these profilograms, because you can then see whether your surface consists of a relatively flat area which contains some sharp asperities on it, or it is more or less smooth surface with some sort of like a dimples or valleys inside the surface, because it would change dramatically the way how this specific surface can perform its duties. Also in the video it was already noticed that you can see that each kind of machining process leaves a different type of fingerprints on the surface, and these are those like an etalons, the similar shown in the video. And you can see that this is a fingerprint of face milling process in different scales, and it goes for a very from a very rough one like here, and smoother, ending up with almost yet again a mirror like smoothness. So you can see how reflection change from sample to sample. Uh, Same type etalons you can have for different type processes. So this is for spark erosion. As you can see, the fingerprint is very different. Now it's very kind of evenly distributed in all directions, while previously it was very well kind of organized in one direction. And yet again, you can see how from the rougher example we are getting to the smoother one here. And yes, this is the first way how to check roughness, is if you have like a specific etalons like this. They cost a couple of hundreds up to a couple of thousand euros, depends on how large they are or how much surface treatments they are having. So like instance here we have 1, 2, 3, 4, 5 different surface treatments on the one like workpiece and etalon. This will definitely cost more than having individual one like this, which is specifically meant for one specific surface treatment. But yet again, then you need to decide whether you are dealing only with one type of production tool and you only need one etalon, or you are producing details in different ways, and thus you need a different type of etalons to check them. And you can look at them and you can rub your nail against them, and you will sense yet again this how rough or smooth it is. And then you can look at on the side of the on the thing, like what is the actual roughness. So if for instance here it says N7 quality, I hope you can see, then on the other side you can then read like what N7 quality stands for. But yeah, we will get to similar cases later on. But this is only kind of brief interpretation of the surface, so you don't get any actual readings from your actual test surface. You can only compare, it feels more like this or more like that other one, and thus you can kind of predict what the roughness of your surface is. But in order to be really precise, we must take measurements by using profile meters, like one there, or yeah, other one next to me right over here. So that is it again, very general information, like why the roughness is so important and why we must deal with it. And now I will start my presentation. So second. So I hope you can see my screen. So this is from the mid-tutorial training program I participated. So basically, I won't be able to give you this presentation because it contains an access key to get it opened, but thus I am encouraging you to like maybe take some notes and listen carefully of what I'm about to discuss here. But as I mentioned, it is possible and it is quite easy to search this information. So I think the main thing is to, while I'm going through this presentation, is to follow the terminology to get the main idea, and then you can look up the information yourselves later on. So this program consists of 14 chapters, and the first one is understanding the micron scale yet again. Then the product line of the roughness measurement tools, we will run through it because it's not the thing on which I'm about to focus now. So, and then there's a surface configuration, indentation of roughness in technical drawings. So what is the skid and skidless type of systems? On that point, we will look a video which is prepared in the YouTube. Then what is profile, filtering, measuring conditions, and significance of the parameters, and then we will very quickly go through different type of parameter subgroups like these motif parameters, VDA standard, because yeah, they are quite specific, to be honest. For instance, this motif standard is pretty much meant for car industry, so maybe you're not very interested in that, but I will just quickly like scratch the surface of this topic so you know that they exist. And yeah, in the end, some configurations, rules of evaluation, or effect of inappropriate filtering, etc., etc. So first of all, what does the micron mean? I hope you already should kind of sense what the micron means. But if you're still having a hard times kind of sensing it, then there is a zoom in for this. So if we take our Earth as a beginning level, so the decimeter is the 10th in the second minus second scale. So this is zooming in, -2, -3. So this is a millimeter comparison. Then we have even lower values, so we can zoom in. Oh, there's an island on the planet Earth, so we are zooming it even more. And there is a kind of sub-island. And we are now zooming onto the beach, which is 10 in the -7th, -8th, and the very last is the nanometer, would be if you would zoom in from the like a whole view of the planet Earth down to seeing sand grain type of deal. So this is humongous zoom in, but actually what if we are speaking about the roughness, then we are only dealing with the micrometer or nanometer scale. That's the thing. If the previous kind of subject topics we discussed used a millimeter as default value, so if there's someone wrote down like 15, you without any like reconsidering should already know that it was meant as a 15 millimeters, because the millimeter is kind of default value in dimension metrology until it gets to roughness measurements. So when we get to the roughness, we are dealing with micrometers and nanometers. So micrometer is kind of more easily associated with something realistic. You can take your hair, look at it, you can barely see it, but the 1 micron is 100th part of it. So you could divide your hair diameter in 100 subcut pieces, and this would be the scale of the micron. So we are dealing with very small measurements, but they can influence our function very drastically. Also, besides the already mentioned examples, now I actually forgot to mention that surface roughness plays a humongous role in the optics. Actually, we are dealing with some sort of a glass in the like the optical lenses you put inside your eyes. They are also very dependent on the roughness, because if the surface is not smooth enough, then you simply won't see through it. And additionally, you might at some point deal with some sort of like a sealing issues. Let's say you need to prepare a vacuum chamber, or you need to do the opposite. You need to pump up some pressure in some sort of like a chamber. Then you also must have some sort of like a sealing. So you have like the main like a cylinder, let's say, and you have a cup on this cylinder, and you need to seal it somehow. And one way is to prepare those surfaces very smooth, very parallel, and then you can physically kind of compress them together with some sort of bolts. But easier way out typically is if you use some sort of elastic material in between. And also why surface preparation is so important in the vacuum kind of applications is because if you want to create a vacuum somewhere in the limited space, you want to simply suck out all the molecules and particles kind of chamber. And it's not hard to imagine that if the chamber walls are very rough, very robust, very porous, then it's way easier for us all sorts of material particles and atoms to simply kind of hide and stuck inside of these porous surfaces instead of smooth ones. So this is the reason why things related with either high pressures or low pressures typically have a higher need for smooth. Also, the surface roughness can initiate fracture of your component. If your component is very rough and you kind of bend it forward and backward, then in one of those rough like wallies, most likely your crack will start to emerge, and this is the kind of weak spot of your component. This is also sometimes very good to keep in mind if you need to kind of aware that your design, product, or detail need to last very long, then you might be interested in paying a bit more effort in trying to make it smoother than you would normally do. So, okay, so what does the surface roughness mean? I've already mentioned many times. So interpretation of how smooth the surface is, and also here you can see like that all of these four parts have the same RA or RA parameter, which is the most typical parameter used in order to measure surfaces. You can see that like after measurements, all of them are quite the same if we compare the measurement results. but it is also, I think, very easy to imagine that this surface and this one and this one and this one will behave slightly different in certain applications. So that's why, besides only seeing this parameter RA, you are very definitely interested in seeing the texture, like how it actually looks like, and thus you have these either microscopic images like here, or you have these profilograms, which I just show you recently, these kind of wavy profiles. So historically, how do you measure them? So the easiest way was to just look at your parts and either touch them, as mentioned before. So it kind of works all right up till a moment when your eyes or your workpiece start to fail you. I guess you all are aware of this image. This is an optical image, which is, it's actually still image, but because of a certain optical tricks, it looks like it's waving. So it means that visual impression can be very unreliable in many cases. So, and also you can only see things up to one moment. You cannot see like a sub-micron scale with your bare eyes, because you can barely see your haircut, and your like a piece of hair, as I mentioned, is around 100 microns. So if you are trying to look at things of 0 point something microns, simply physically impossible. Thus, the equipment is needed in order to measure it. So, how do you deal with the measurement problems? You purchase yourself one or another type of measurement tool, and they can be portable, very simple, kinda, very cheap, kinda. Typically costs around 1.5 to 3,000 euros per unit if you want something like this. But if you want to go for something more advanced like here, then the sum of the tool typically grows up till tens or sometimes hundreds of thousands of euros. And if you want to do it with a non-contact measurement tools, yet again, there's two ways how you can measure. As mentioned in this video, I showed you, you can measure them like with the contact type of profile meters, like shown here, when you physically are sliding across the surface with a needle, very tiny one, or you can use some non-contact methods like confocal microscopy, laser interferometry, etc. And actually, I guess maybe you haven't heard of the profilometers as shown here, but I guess all of you are aware of atomical force microscope. So this is actually the same as the profilometer, but the difference is that atomic force microscope is way more sensitive and way can like get into the way smaller details than the profilometer. So basically you can imagine profilometer as a big brother of an atomical force microscope. So here, this is just an upgrading level. So yeah, this is the very small tools, a larger one. Then we have one like next to me over here, and it can go up to a very complex and expensive systems like that. So the thing is that any workpiece, regardless how smooth it seems, it has some sort of deviation from the geometrically ideal shape, which is true for everything in this planet. So nothing is smooth, nothing is flat, nothing is straight. So thus we need to specify these straightness, flatness, roundness, and etc. tolerances. So we are defining the limits which are acceptable for our needs. So if you are just cutting some sort of like a firewood that it does plus minus 2 or 5 centimeters, doesn't matter until you can put it inside your fireplace. Or if you are preparing like an artificial human teeth, then you have a very limited space in your mouth in order to put it in. So thus your tolerances must be way lower, and the same is also here for a surface roughness. So yeah, I guess that's that now. So, and what is important? So basically, how do you measure these deviations? So if this is a kind of sketch of our surface which we want to measure, the most typical and least expensive method is using these profilometers. And the profilometer works basically as it has this stylus. In the end of the stylus you have this needle over here, and this needle simply slides across your surface like this. And basically what it does, it copies your surface, then it magnifies it like many times, like in the example shown before. These surface oscillations were magnified 5,000 times, sometimes it's 10,000 times, and sometimes even more. So you can now see these oscillations in a very magnified scale, and thus you can analyze what is what on your surface. So you can already see some sort of blue lines, some red lines, but we will get to that in a while. And now we need to understand what the surface profile actually is. And before we do that, I am suggesting a small 5-minute break so you can cool down a little bit, and so I can drink up my water because my mouth is already dry, and we continue after 5 minutes. So now it's just a small break for all of us.
Great, thank you.
So our 5-minute break has lasted, so I'm about to continue. I hope you all are also back next to your screens and you can hear me well. So what is surface profile? Because this term surface profile will be used many times if you want to speak about surface roughness, texture, etc. So first thing is we can have a contour line. Contour is basically large deviation, like a large wavelength. So you can actually imagine the surface as simply as an oscillation. So, and the oscillations with the longest, like the period, are called the contours. The bit smaller ones are form deviations. So you can now see that you originally intended to have like a curved surface, but in the end it turned out to be slightly deformed. On top of that, you can have oscillations with even smaller wavelengths, so they are called waviness. And the last component is actually a roughness, and basically we'll combine all of these three four components: contour, form, waviness, and roughness. You actually get your primary surface which you just measured. So in reality it looks like this. So if this is your scanned profile which you measured by using one of those profile meters, first of all you can level this profile. Let's say if your workpiece you measured is not parallel, but it's some sort of like a slightly tilted one, then you simply want to just kind of level the beginning and the end of your profile so they are on the same line and they are horizontal. That you obtain this primary profile, and then you are using filtering operations, which we are about to discuss a little later. And from that, using these filters, you can divide this primary surface into subsurfaces. So the waviness, which is called simply waviness typically, and you can have a roughness profile, which is the roughness. And basically, if you mathematically add these oscillations on top of these, you get yourselves a primary profile. So is this more or less clear at the moment? That is a question for you guys and girls. I hope so. So basically, yet again, step by step. So if this is a very magnified cross section of our part which we produced, then we can look at this profile as a kind of different wavelength oscillation combination. Those waves with the longer wavelengths, so see, this is the period, so this is the middle line of the profile, so the oscillation goes up, then it goes below zero line and goes up again. So from here up till here we have a one period of oscillation. So this is the wavelength of the oscillation, and the components of the profile which have a longer wavelength, so this gap is longer, are considered waviness, and those oscillations which are smaller in the scale, in the length, are considered to be as a roughness component. And depending on your application, sometimes you are interested in looking at the primary profile, sometimes you only take care of roughness, and sometimes you are more interested in the waviness itself. How to divide them? We need to use filterings. So what does those filters do? Basically, you choose like this threshold value. So if I'm going back, let's say I can now choose, okay, if the distance from here up till here is, let's say, 0.8 millimeters, then I was the one who chose that all the oscillations above 0.8 millimeter wavelength will be considered waviness, and everything below this will be considered a roughness profile. And basically, this is what's shown here. So this is our primary full surface. Then we are kind of choosing this kind of interaction point. So everything below this our chosen value is considered to be roughness, and everything above it is considered to be waviness. And this is how the filtering is applied. This is a very mathematical basically calculation. I won't get into that because there's absolutely no point of view of like really like getting it. But what is important for you is to understand that you choosing simply the wavelength of your component, and how to choose it. You don't choose any random number. There are standardized recommended values, and we will get to that. And I think one of the most important points you need to take out of today's presentation is if you are about to deal with surface texture or roughness measurements at a certain point of your life, you really must remember that these cutoff values, which are represented like this lambda c over here, are very crucial in order to do your measurements right. Because if you choose this cutoff value randomly, like just out of blue sky, there's almost impossible chance to do kind of repeatable measurements. Because if the one guy who, let's say, produced this part chose the cutoff value, and you choose your own, it will very dramatically change the overall profiles you will obtain. But this will be farther on mentioned and shown in examples, and I hope you will all understand very well. So, okay, and again, this is not that interesting about filters. Yet again, I guess I can skip it, but so what is interesting is this part. So basically, what you can do, first of all, there are primary kind of filter applied. This is this lambda S. It is a noise removal filter. So usually you, as a person who measures the surface, you won't even notice that this filter was applied, because it kind of goes without saying. What this filter does, it simply removes a very random and very small oscillations, which might be like a result of some sort of like a vibration of your tool itself. Let's say your measurement tool has like a cooling system, the ventilator, and it might produce a small oscillations, and your measurement is so sensitive that you can actually feel these small oscillations. And for instance, this specific measurement which we have here, while it's measuring something which is off the ventilator in order to reduce these small oscillations, but regardless of that, it anyways applied this small kind of noise reduction filter. And if you compare this scanned profile and this primary profile, you can't actually tell any difference because those oscillations are so tiny that you can't most evenly see them even with this like 5 or 10,000 times of magnification. While the different cases when you apply these lambda C, also known as cutoff filters, this is where you can either achieve this roughness profile. So basically, if you want to remove these red line curve, which is kind of shows the waviness of the profile, so you're not interested in that, you only want to see these micro oscillations, then you are using lambda C and telling to the software I only want to see roughness profile, and in the end you will get a profile like this, and you can easily see this is not exactly the same as this. And the same is true if you are interested in the waviness component. You can kind of skip roughness part, which is shown here, and only focus on the waviness itself. Where does these things matter? The roughness typically matters more if you are, in your case, dealing with like the bacteria capability to kind of squeeze in between these small oscillations and start to grow there and anything. While the waviness is a bit more important into the optics, because if your glass, like your lens is wavy, it may deform the image you're about to see. So if you're in the optic kind of field, then waviness might be a very crucial stuff for you. If you're in a kind of bacterial surfaces, then roughness might be more interesting for you. And yes, yet again, so this is the kind of review. And that on the drawings you can find a different letters. So this RA or RA was mentioned already in the video. This is the most typical roughness parameter used, but you can see it has this letter R here. There we have a letter P and letter W over here. And simply, if you know that the full surface consists of primary profile, which can then be separated into the roughness and waviness, by showing on the drawing either P or R or W, you are highlighting which component you are interested in the measurements. The person who will actually perform the measurements will be able to know either to filter off waviness and look at the roughness, or should he or she filter off the roughness and look at the waviness, or nothing needs to be filtered off and you are looking at the primary profile instead. So this is a kind of not very hard to understand. So P stands for primary, R stands for roughness, W stands for waviness. But in order to understand it, you simply must know these terms: primary, roughness, waviness, and this consists of both of these together. Yeah, and there are plenty of parameters, more than 36 of them. We'll get to some of them after a little while. So, okay, and I already mentioned that these things must be specified on technical drawings. So in order to do that, we are using a unified symbol, and this symbol looks like a square root kind of sign, but it may or may not contain this upper letter here. The very universal symbol is just square root type of symbol, and there are plenty of places where you can add some additional information. So in the where letter A is, you write the number of cutoffs, parameter, and limit values of the roughness parameter. So this is the most crucial area typically shown over here. So on the area C, you can have production process information. On the area B, you have additional roughness parameter on the roughness of the rough information. So it means that this list over here, A, can be continued down until you write down all the information you really need to take care of. D is indication of the surface grooves. So your surface grooves might be parallel, perpendicular, etc., but we'll get to that. And machining allowance. So these are information about the machining process. So step by step. So basically, this is the type of production. Could be grounded surface, and this is the name of the production. Here we can see direction of surface grooves. In this case, it should be measured perpendicular to processing direction. And here are some information about the parameters. So L means the lowest specified limit. H would stand for highest specified limit. X is type of filter. There are typically these RC or Gaussian filters, two of them used in pretty much 95% case, I guess. These Gaussian filters are used. So in that case, you would write down capital G there, but this most likely you won't use them anyways. So there are some sort of additional information, but what is very important is this surface parameter RA, and the value is 5.0, and this 3 means the number of sampling lengths. What is sampling lengths? Yet again will be shown. So basically for you, I think what should matter is most likely only this end part of the whole thing, and sometimes this direction of the surface groove is very important. So here are different examples how it could look like, and it is very important that you put this kind of square root sign or the roughness symbol on the specific surface which needs to be checked. You don't apply it to all of the surfaces, but you only apply it to the surfaces which really need to maintain a certain quality. And the reason for that is, because it was mentioned in the video, this kind of costs a lot to produce very smooth surfaces, and you don't want to spend too much money if you don't actually need to get some sort of performance out of this surface. As I said, the general symbol is only this kind of square root symbol without any line here or circle here. You are always allowed to use this general symbol, like only these 3 lines. But if you add this line on top of it, it means that some material will be removed from the surface in order to create the final texture of your workpiece. So for instance, if you are milling something or doing some electro erosion and stuff like that, you are actually removing some material up till the point when you achieve the desired surface quality. And if you apply this line on top of here, you are kind of saying to the producer that you allow material removing in order to achieve the final result. While if you are showing this circle inside here, it means that material won't be removed, it will be only deformed in some way. For instance, for shot peening, you are just blasting the surface with a small kind of shots like bearings, or you can do a rolling when you kind of just flatten the surface, kind of squeeze it, thus making it smoother and so. And this is like a twist free. Basically, this is a general symbol which is used when you don't kind of care whether the material is removed or not removed. You only care that the final quality is as you expected. Uh, Regarding the orientation of the measurement, you might see symbols like here, here, and here, and so on. So this means that your measurement must be taken parallel to the plane of projection of the view in which the symbol is used. So if you have kind of process markings in this direction, you want your measurement to be performed parallelly to them for some reason. If you want them to be measured perpendicularly to the shown direction, then you add this perpendicularity kind of symbol. X means that you have a crossed grooved surface, so it means it looks some sort of like a cross, and in that point you kind of don't care that much in which direction the measurement is performed. You might have a multi-directional surface, which stands for M. So this is the point when the person who measures kind of decides in which direction to measure. But there's one very important, like two very important the rules but recommendations from ISO standard, what to do in such these cases when you are kind of allowed to choose the measurement or orientation. In those cases, first of all, you are always trying to do a measurement perpendicularly across your processing scars. Let's say you have a very obvious scratch marks in one direction. It means that in order to perform the most reproducible roughness measurement, you want to measure it perpendicularly across those measurement scratch marks. And the second advice is that you kind of want to measure the worst produced area. If you have like a certain areas which looks very smooth, and for some reason on the same surface you have some areas which are not very smooth, you kind of need to measure the worst area to kind of check if the worst area suits your requirements, that also the good one will definitely suit. So these are two kind of recommendations, but sometimes people are not following them because maybe you have a very nice surface in general, but during transportation on the one area you see a little bit of a scratch marks, and maybe those scratch marks simply don't mean too much to you, and they don't infect the components like a functionality. And then you can kind of skip measuring this worse area and just simply focus on the any other area on your workpiece. So besides these ones, you might have approximately concentric surfaces. Actually, I have example here, but it will be very hard to see. But okay, that doesn't matter. But you can see that let's say, for instance, from if you're using a latte, then you are lathe machine, then you are producing a surface like this in the cross section. For milling, you might achieve a radial surface when your cutting tool is moving in a trajectory like this. And the last one is non-grooved surface on directional or pitted. So basically, let's say if you are shot blasting the surface, you're like millions of small particles which are bombarding the surface will produce it randomly oriented, so doesn't in that case it simply doesn't matter in which direction you are measuring your roughness on the part. Uh, yet again, some examples. So this is how a technical drawing could look like. You could have a surface. On the surface you show the symbol. By adding this additional line, you are saying that the material must be removed in order to achieve a roughness parameter 0.6 Ra, and Rz should be 0.2 or better. And additionally, you can add tons of other stuff you want to measure, but I'll be honest, it is almost impossible to predict, but to produce parts which ask for various texture parameters to match the certain requirements, because a lot of those parameters are mutually related. If you change one, the other one changes accordingly, and thus you can only stick to the one which is the most important for your case. Okay, and now skidded and skidless systems. So basically, I think now I am stop sharing this screen and I am showing you one small video which pretty much explains the same thing. And after that we are having a break, and after that we continue as always. So this video explains you like what's the difference between skidded and skidless tools, and show you some examples, and then we will review it once again in the presentation.
America Corporation. I'm here with Jeremy Banks, and on today's tool tip, we're going to be discussing the difference between skidded and skidless surface finish measurements.
So, Drew, many of my customers have questions on when to use skidded versus skidless surface finish.
Right.
So, do you think you could take a couple minutes and explain what the difference between the equipment or maybe some different uses that you would have with these devices?
Absolutely. And to start out, before we really get into the difference between skidded and skidless, let's take a look at what the components that make up a surface finish gauge.
Okay. So, Drew, what equipment do we have here right now?
So, 2 units. I have a skidded and a system.
Okay.
These are both made by Metrology, but these could be, in effect, any brand of surface finish measuring system. All systems are made up of the same components. You have a stylus, and the stylus is the piece that contacts the surface to do the measurement. The stylus feeds into a detector. The detector takes the movement, translates it into a signal that can be measured, and then we have the drive unit, which pulls the stylus and detector assembly back and forth for the measurement. That'll plug into an amplifier, which is where you get your readings from. Now, this is a skidless system, as I mentioned. The skidded system is very similar, except you'll notice that the stylus and the detector are all one piece here. So I still have the stylus that's protruding out from the detector, but around it is a housing, and that housing is what we refer to as the skid right here.
So what's the purpose of the skid?
The skid is going to act as a mechanical datum for your surface that you're measuring. On a skidless system, that datum is actually inside the drive unit. So you're going to find that most entry-level systems are going to be the skidded unit with the housing around the stylus.
Now that I understand the physical differences between the devices, what are some different applications?
Great question. So let's take this pen, for example. That doesn't have to be any customer application, but it's a piece that somebody needs to measure surface finish on. Okay. As I'm looking at this pen, there's really multiple areas that can be measured. We can measure the top face. We can measure along the axis of the pen. We can measure over the radius. And that's really going to make a difference which unit we use based off what needs to be measured on here.
Okay, well, let's just say I wanted to measure along the axis.
Okay, so if you're measuring along the axis, a skidded unit would be great, because what's important with the skidded unit is that after it makes contact with the part, that the skid is always in complete contact with the surface that's being measured. So if you look at the skid here, there's no gaps between the skid and the part anywhere. It's not sitting at a kind of a weird angle to where the beginning or the end of the skid is off. It's nice, even contact, to where if I were to move the stylus or the skid back and forth, it's always in contact with the part.
And that's important because the skid is the datum, and if the datum isn't making good contact with the part, you get inaccurate measurements. Right?
That is. So if you were to measure along the axis of this part, you'd be fine. If you wanted to measure the top face of this part, you'd be fine as well.
What if I wanted to measure radially?
That would be an issue with the skidded system. So let's flip the part up here. Now if I were to present the stylus to the area, as I move the stylus back and forth across the part, you notice depending on where I am, either the beginning or the end of the skid are going to be for the surface that's being measured. Right? I'm either going to have a gap at the beginning or gap at the end of the measurement.
Right, and this would be bad because that's the datum and it's not making consistent contact with the part.
That's correct. Now, if I were to take a measurement with this, I could probably spend some time with the setup and actually get a number that's going to show up on my amplifier, but that doesn't mean that the number is a good measurement that I can trust.
Okay, so in an application like this, a skidless system would be better?
That's correct. So you'll notice as I bring a skidless system in for measuring, that by having a skid, I can actually bring the stylus in contact with the surface. I'm going to get a very good measurement here. You're going to be able to trust these numbers that you're getting from this unit.
So as long as I stay within the stroke of the detector.
That's correct. Okay. That's correct. Depending on the unit you have, that will vary how much actual stylus travel.
So as long as I stay within my stylus travel, I can measure radially across the part.
That's correct. That would be no issue to actually have the stylus traverse from side to side. Obviously, I'm moving the whole drive unit here, but in an actual measurement process, it would just be the detector moving the stylus.
Drew, that makes sense, measuring round parts versus straight parts. Are there any other features that would lend themselves to a skidless device versus a skidded?
Absolutely. So let's switch parts for a second. And now we're going to take a look at the piston. The piston has a small groove here on the outside diameter. If we wanted to measure this groove, it might be a little difficult to do with a skidded system because as I start to move my stylus in, you notice the skid is larger than the groove that I need to measure. So I could not actually measure the bottom surface of this groove with a skidded unit. However, if I bring my skidless system in, now you'll notice I can easily not only reach the groove that needs to be measured, but I still have room to measure from side to side along that groove.
So let's say that I have a part with a groove that's a little deeper. It's a little more narrow. Is there some flexibility in the type of styli that I can use?
Absolutely. With both the skidded and the skidless systems, there are different styli that can be used with that system. So if you need to reach deeper within a part or down within a groove, maybe at a little bit of an angle for a geared tooth, we can accommodate for that.
Okay.
There are more styli options available for skidless systems than there are for skidded systems typically, though.
Okay. So other than the physical limitations of the workpiece, is there any other reason that you would use a skidded versus a skidless?
It's going to come down to what parameters you're measuring. And when I say parameter, most folks are familiar with terms like RA, RQ, RZ. Those are the parameters that you're actually measuring with the surface finish gauge. Because it starts with the R, it's a roughness parameter. Any gauge, whether it's skidded, skidless, can measure the roughness parameters.
Okay.
If your parameter starts with a W, it's a waviness parameter. We can't actually measure waviness parameters with a skidded unit because the skid itself will mechanically filter out the waveform. So if we're going to look at waviness, WA, WT, or common parameters, we have to start with a skidless system for those measurements.
Okay, great. I've got to ask, if the skidless system seems a little more versatile, why would someone purchase a skidded system?
Typically, your skidded systems are going to be your entry-level systems.
Okay.
They're going to have a lower price point on the initial system. Once you get into the skidless system, though, you'll find that the replacement styli are going to be less money than a skidded system because on a skidless, the stylus is a standalone as to where skidded, the stylus, and the detector are both one body, one housing.
Okay, so if I have a simple measurement where I just want to measure a flat piece for an RA, a skidded or a skidless would work either way.
That's correct.
And if I want to start measuring on parts or I want to measure grooves, then I might move into a skidless system.
Exactly. And when in doubt, feel free to give us a call, look us up online. We'd be more than happy to help determine which is the best unit for not only your application, but for your budget as well.
So, I showed this video because, in my opinion, it very kind of nicely highlights the most important, like the differences between them. But now we are having first a large break, pause, and basically, as always, we meet up after 1 hour. So basically, yeah, on the 1 o'clock. 15 minutes before 1, we continue with our presentation. And yeah, so now it's just